CO2 and hydrogen. Okay? Now, let's say hydrogen has 7.5 kilomoles. It's at 40 degrees C and 400 kilopascals. And CO2 is the 2.5 kilomoles, 27 degrees Celsius, and 200 kilopascals. So I have two separated gases at different temperatures and at different pressures, and they're two different gases. So when I listed kilomoles, what is that? Well, wait. Let me write all the inputs and then we'll talk about it. What is the other one? The constant volume, the specific heat at constant volume for CO2 is equal to 0.657 kilojoules per kilograms Kelvin. And CP, CV, we're going to use the CV here. CV of hydrogen is equal to 10.183 kilojoules per kilograms Kelvin. So these are your inputs in general. I guess the problem is remove the boundary. And find final temperature, pressure, enthalpy, entropy generation, calculate the our fine mass and mole fractions. And we're going to find the total molecular weight as well. So everything that we just covered right now, we're going to compute it with this problem. So I have two separated gases, and there are different conditions in terms of pressures and temperatures. I'm going to mix them. There is no reaction, but they're obviously at different temperatures. Is the entropy generation equals to 0? What if they're equal in the same temperature condition? Well, let's get to that later on. I'll talk about it once we compute it, but we'll think about it as we go through it. What if they're at the same pressures and the same temperatures? Do I have entropy generation?
Yeah.
Who said yes? Why? It has to be explained for it, but okay? So people think about it as it goes through. You know, they're not reacting, right? So they're at same temperature, same pressure. It's you're getting close, getting warmer. Very close.
Entropy increases because the gases mix together and it's not easily.
What?
The gases are all mixed together and so it's a pain to get them separated once they're mixed.
Yep, right on. That's it. So what your colleague mentioned is if I have two gases that at the same temperature, same pressure, I just remove that barrier all of a sudden and they diffuse together, right? they're not going to react. I'm not going to get energy. But I do have entropy loss. What is that entropy represented in? That entropy is the amount of energy that it will take me to separate that gases again apart. You have to do work to separate these two gases, right? If I have two gases mixed together, I have CO2 and hydrogen mixed together, and I want to separate them, what do I need to do? I have to do some kind of work. It's an irreversible process. So I am going to have entropy generation because they are going to diffuse together. I have to do work to separate them again. Does that make sense? So I'm picking the example primarily that the two different temperatures because I want to capture that different temperature behavior. But in reality, if they're the same temperature and the same pressure, you still have entropy loss. And the entropy loss is the fact that the two gases diffuse. Now, to separate them, I have to do some kind of work, separate them by temperatures and condense one gas versus the other, and then separate them separately into two different tanks if I wanted to. So there's work in that I had to do versus simply by removing that boundary, I took two ideal gases already separated and mixed them. So think of the car engine, for example, when we said heat going to work 100%. Well, that's not possible because I get heat losses. That heat losses I'm not getting again. That's the same principle. It's energy that is lost. But anyway, back to this. 7.5 kilomoles and 2.5 kilomoles. What does that represent? So I intentionally written the numbers. I didn't write it. What is it exactly? N of that species. Right? So this is N of hydrogen is equal to 7.5, and this is N of CO2 of that specific species. Okay, so let's solve the problem. You have to make assumptions first. Well, what do we have? We're going to assume it's ideal gases. We're going to assume my specific heats, both constant pressure and constant volume, are constant. So constant, CPs, CVs. I'm going to assume I don't have any changes in my kinetic energy or potential energy. What else? It's adiabatic because it is insulated. And no work done. I don't have any shaft work or boundary work. So, want to find final temperatures and final pressures and so forth. Well, what is the equation for that? How do I get my final pressures and temperatures? What is the equation that I use to get pressures and temperatures that I always use? Ideal gas law. Very good. So, ideal gas law. I just want the final one. So what does that mean? Well, it's simply my total. So, pressure total multiplied by volume total is equal to N total multiplied by my universal gas constant, T total. What do I really have out of those? Well, I get N total. That's easy. I don't know what P total is. I don't know what the volume total is. I don't know what the temperature total is. So I'm just going to say this is equation 1. I have too many unknowns here, but it's one equation that I'm going to use. Okay, so how do I get some of these properties? I will say V total is equal to the volume of each individual gas that I had initially. If I know the volume, yeah, you can see it, the volume of CO2 and hydrogen, then I can determine that. Well, what is the volume of each individual species? It's V of CO2 plus the volume of hydrogen. And they were separated. How do I get the volume of each individual species? Oh, sorry. Can you see it? I want to keep the problem, but I'm running out of room here. Why does that menu? Okay.
Ideal gas.
Very good. Ideal gas law again. So ideal gas law is going to equal to, so V total, and you probably don't see it now. I'm just going to move it and we're going to reference to the problem as we keep going. You've written this, right? Okay. Okay, V total, use ideal gas law. Well, it's the same principle. I will say N CO2 of my universal gas constant multiplied by T of CO2 at what stage? It was an initial stage. They're going to get to an equilibrium temperature, but initially it's at T1 divided by Q of CO2 at stage 1 plus N of, what was the other species?
Hydrogen.
H2, sorry. RU T H2 1 divided by P H2 1. Okay, so do I know this? 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 And I know this? And I know this? Can I get my V total? Yes. So from this, you can just say this is my second equation of how do I get V total. Okay, so how do I go and determine each individual or final temperatures and so forth? I need other equations because this gives me only this. And this I can get because it's sum of number of moles, so I know this, and I know this. I need to know the final total temperatures and the final total pressures. So I'll have to use the first law, thermo. And what does the first law say? Well, rate of change of energy is equal to Q net plus work net. Do I have Q? I said it's an adiabatic process. Equals 0. And I said no work done. No work. So what does that say is the rate of change of energy is going to equal to E1 is equal to E2. Hence that equation that I just listed in terms of difference in energy, internal energy. So from there, I could say N of CO2 multiplied by E. Now, which E are we talking about here? Bar, very good. Because I use the mole fraction, or sorry, the moles, number of moles, plus the hydrogen multiplied by the internal energy of hydrogen at stage 1 is going to equal to my final N CO2 of and the energy of CO2 at stage 2 plus N of hydrogen multiplied by E of hydrogen 2 at stage 2, or H2 at stage 2. So what am I saying here? Well, since it's not reacting, I could bookkeep my number of moles. And by bookkeeping my number of moles, I do have an internal energy change. But the moles are the same equation that we listed earlier, right here. I did it in terms of mass, but now I'm doing it in terms of moles, right here. This same equation. because it's non-reactive. So I could write the general form of that equation and say NCO2, so combine some of these terms, and let's move this one on this side and this one on that side. So it'll be E1 CO2 1 minus E CO2 2 is equal to NH2 multiplied by the internal energy of H2 at 2 minus E of H2 at 1. Now, we typically don't work within the internal energy stage, so what is internal energy equals to? CV delta T. So I could say NCO2 multiplied by CV. Since it is constant, I don't have to worry about it changing from one state to another, because the delta and temperatures are not large enough that it's not a function of temperature. So I could say CV CO2. Now, if this is in terms of moles, I'll keep the bar up there and say it's T CO2 1 minus what temperature? Somebody said T total. Very good. NH2, CV of H2, bar, and T, what? Total. It's going to be reaching an equilibrium temperature. You have two temperatures, they're going to mix. You're going to reach to a steady state, which is the final temperature. They're both going to be equal. Minus TH2 at stage 1. Okay, so let's box this and say equation 3. So what do I know? I know this, 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 and I know this. What can I get out of that? T total. Now, we already listed CV